All right, electrostatics. Okay, this is your intro to electrostatics. So, you guys played with the Van de Graaff generator before?
Yes.
That's the really fun thing at the end, okay? We'll play with that when we do video 4, which is at the end of your packets that you have, okay? Okay, so here's what we want to be able to do. We want to understand the basic structure of an atom to understand electrical charge, okay? Now you guys learned a lot about this if you took chemistry, okay? So we'll kind of get into that a little bit. Conservation of charge. We already know about conservation of energy and momentum, okay? There's something called conservation of charge too. Conductors versus insulators. We've heard these words, yeah? Okay, we'll study that a little bit. Understand differences between charging. Okay, there are different types of charging. Okay, here they are. We'll learn what those mean. And know the definition of a coulomb. Okay, and Coulomb's law. All right, that's what we're going to do in the first part of this unit. Okay, so what you learned in every science class, yes? You guys have seen this before lots of times. Subatomic particles. You got the electron, proton, and the neutron. Okay, so some notes on your note organizer there. Electron we know is a negative charge. We indicate that with a little minus sign out front if we're talking about the charge. And the mass. You don't have to memorize that.
Is that given to us?
Yeah, well, it's on your constants page, if that's what you mean. So what you guys can use on all your tests and things like that, this mass is on here. It goes for every electron. It's 9.11 times 10 to the negative 31st.
That's really small.
Okay, really small mass. That's in kilograms. Okay, just like we measure the mass of all our things in lab in kilograms, even though electrons are so small, still measure it in kilograms. Okay, protons, positive. And our mass, still very small. 1.67 times 10 to the negative 27th. Okay, have you guys become friends with scientific notation yet?
No.
Come on, I've been telling you to do that for a long time.
27.
You don't want to be writing out all those zeros, okay? All right, neutron. Do you guys want to hear my neutron joke?
Sure.
If you know it, don't finish it. Okay, so there's a neutron. It's walking down the street, walks into a bar, says to the bartender, "Give me a milk." Bartender slides the neutron a milk. The neutron enjoys the milk, drinks it up. Says, "Bartender, how much do I owe you?" Bartender says, "For you, no charge."
I feel like it wasn't milk.
That's it? That's the joke?
No shit, that's the joke. That's okay.
No, get out.
No charge. No negative, no positive. Neutral.
Yeah.
So what?
Everyone's like waiting.
You guys were waiting for me to finish the joke and I was already done. That's sad. Okay,
It was
mass.
so funny, it made me sad.
Look at this. Same. Okay, 1.67 times 10 to the negative 27th. Okay,
So
if
the
you take physics 2 next year, you will learn that an electron and a proton are fused together to make a neutron, which is kind of weird, okay, thus canceling out that charge. All right. Okay, how many of you took chemistry? Okay, a handful of us. All right, in chemistry, or probably before that, you guys learned about ions. Ions just means the charge is imbalanced. So 6 positives, 6 negatives, this is not an ion. Balanced charge, that's not either. Okay, 0 net charge. Okay, what if we do this? What if we take 2 of the electrons away? Or what if we add 2 electrons to this atom over here? Now we have an imbalance of charge. Okay, so we have a positive and a negative 2 net charge. This would be called a positive ion. That would be called a negative ion, or what else do we call negative ions? Anion, that's right. Okay, these are called cations. All right, so let's say we have these ions here, positive and negative one. What we're going to do, we don't even really care about the whole atom. All we do is simplify them to positive and negative. Okay? Now I wanted to put that up there so you guys saw that, hey, here's what's really going on. It's actually, we got these atoms and they're imbalanced, but we are not going to draw atoms in this class. Okay? You guys already did that in chemistry, or you will when you decide to take chemistry. We're not going to look at the Bohr models and all that. We're just going to say, oh, okay, over here we can have positive charges and negative charges. All right, we simplify a little bit down to this. Okay, now you guys probably know this. Like charges do what? They repel. They don't like each other. So negatives hanging out with other negatives, they have a tendency to repel. Okay, positives hanging out with other positives, they repel. They go away from each other if they can. Okay, and then opposite charges attract, right? Okay, there are forces between them. So let's take a look at let's prove it a little bit. All right, so over here we got some different things. First of all, we have Edgar. Okay, why his name is Edgar? The details are fuzzy. I don't really remember. One day his name was just Edgar. Okay, no, I did not shoot Edgar myself. Okay, Edgar came from New Zealand. It was a gift, and then it ended up in my...
Tasmanian devil.
Not a Tasmanian devil. Okay, good guess. All right, any other guesses? What is Edgar?
An animal.
A mammal, yes.
Is he a marsupial?
Nope.
Is it native
Nope.
to New Zealand?
Well, I won't say native,
from
but this
Australia.
came from New Zealand.
Oh, I thought it was Australia. I'm confused.
Well, what's the significance of
Not a honey badger.
Is it one of those
Really happy animals?
Is it a marsupial?
Oh my
No,
god.
it's not a marsupial
Is
of
it a
any kind.
mammal?
You guys will just have to keep guessing later.
It's a dolphin.
But I won't tell you until you get it.
Can't think of
Okay, now here's the reason why we like Edgar. Edgar will give us negatives. Okay, so this is made out of plastic. Okay, it's kind of rubbery. If I take this and go like this, okay, give Edgar a nice back rub.
That's creepy.
What? Come on, it's not creepy. Okay, just give an Edgar a back rub here.
He's
It's
dead.
no big deal.
It's not even a thing anymore.
He is dead. Okay. Now, what's happened when I do that is I have literally taken electrons from Edgar and now they are on here. Okay? What this is made of clings on to electrons better than Edgar's fur. Okay? Does that make sense?
So it's tricky.
So I'm literally wiping electrons off of Edgar and putting them on here. Okay? You guys see the little electrons running around on there?
Yeah.
Yeah.
Okay, that's the weird thing about what we're studying is you can't really see it. So we can only see the effects of it. So I'm going to take this and hang it from here. Okay, I'll clip that on. Now what's the charge of this?
Negative.
Negative. Okay, we'll try and get this kind of balanced. Okay. That's pretty good. Okay, that's negative. Alright, now I need a balloon. Let's see. Okay, now I used to use students' heads to charge this up, but now I have Edgar, so I don't have to mess up any of your hair. You would have been prime, right? Yeah.
Josh's hair would have broke the balloon.
Okay, now this is made out of plastic too, basically, right? Rubber?
Yeah.
Okay, I'm literally wiping electrons off of Edgar onto here. Okay, so these two things are opposite, right? So if physics works, what should happen here?
Should repel.
Repel.
Should twist.
Should repel, okay? Oh my gosh, look at that. Okay,
No freaking way.
okay, now we have created a what?
A mag.
A force. okay? We're still going to be talking about newtons in this unit, okay? This is called electrostatic force, all right? And it's a repulsive force. Okay, now, here's something kind of weird. This one's made out of glass, okay? And here we've got silk. It works differently though. So if I go like that, this time the electrons stay on the cloth, okay? So I am taking electrons off the glass, and now there's a bunch of electrons running around on here. So this is what charge?
Negative.
And this is?
Positive.
And what's Edgar?
Negative.
Positive. Okay, and the balloon is negative. So now if I take this over here, what should these things do?
Attract.
They should attract. Okay, so let's see. Okay, it's not quite as strong, but you can see, you can get this thing spinning this way.
What happens if you touch them together?
Okay, that's a good question. Now some things, if you touch them together, you'll get the charge to transfer, okay? So if I touch these together, was there some transfer of charge?
Sure.
Yeah, probably. Maybe not completely though, because these hang on to electrons pretty well, so they might not jump that great, but let's see. So there's still some leftover charge. It's still kind of attracted. Alright? But yeah, there was some transfer there. Okay, now, if you guys invite a guest over to your house, okay, they come to your house, they come in the door, you don't really know them that well, they're not necessarily your best friend or anything. Okay, how do you entertain them?
You feed them.
It's 2015. Well, yeah, you give them food,
Mines.
but that's been, you always do that.
Hire,
Maybe you show them a cool YouTube video.
hire a clown.
No, you don't.
You hired us.
Okay? Maybe, I don't know, you maybe play a video game with them.
And they had.
Wait, are you talking about like adults or
I'd be
like?
why do you have a clown?
Yeah, it'd be
That's
weird,
the
right?
last thing.
Okay, now the reason why I ask you guys this question is because back in the day, before they knew the physics behind all this, people sort of figured out that, hey, if I do this, and then put it up next to this, it attracts that and it moves it, okay? Before they knew the physics, how did that,
Wizardry and witchcraft.
wouldn't that be super cool? It seemed like magic, right? Wizardry, sure. Okay, so these things that we're doing up here used to be literally like parlor tricks.
Parlor.
Okay?
Parlor.
Yeah, back when there were parlors. Okay, you invited your guests over and that was the entertainment room. People took this kind of stuff out and actually played with it. It was like, look, I can do this. Okay? And they thought it was super cool.
That's weird.
Isn't that weird?
Edgar's a red panda.
Not red. Okay. All right, back to this. Okay, Emily, we put that back on the screen there.
Yep.
Okay, so
The lighting's a little messed up. I don't know if you
okay.
wanna. There.
So we just proved there's a repulsive force between electrons or protons, okay? And there's an attractive force between electrons and protons.
So many names.
All right, that's our opposite subtract thing. Okay, now the question is how much force? How do we measure it? Okay, we know how to measure friction, right? It's mu times normal. We need to know the surfaces and the normal force. Okay, what about with this? Okay, how much force? We'll actually get to this in part 2. Okay, but before we do it, we first need to define a certain quantity of charge. Alright, how do we define charge? How do we work with it numerically? Okay. A dozen means what? 12. What about a baker's dozen?
13.
13. I wonder why. Okay. A ream. That means 500.
Whoa.
A bushel is a word that means a number. Okay, a bushel means that many cubic inches. Okay, what are some other words that mean numbers?
Couple.
Couple. Pair.
Few.
Case. Bottle rockets, what do bottle rockets come in?
Packs.
No. Well, yeah, a pack is 12. A bottle rocket. Have you guys ever driven to Wyoming and bought bottle rockets?
We're not delinquents.
You haven't lived.
But I didn't look to see what they was like.
That stuff is probably.
Okay, they come in a big brick like that. How many are in there?
500. I don't know. Rick?
Oh, I think it was on candles.
Not Roman candles. Okay, 144. 144 is a gross. Have you guys ever heard that?
A gross of bottle rockets.
A gross of bottle rockets.
Never
Yep.
heard that ever.
Okay, next time you go to Wyoming and buy bottle rockets, check it out.
Give me
Okay, now another word that means a number, but a little bit more confusing because it's a huge number. Okay, what about this much charge?
A lot.
That's a lot of charge, right? Okay, that much charge is called a coulomb.
How many charges is it?
How many charges is it? Good question.
3 billion.
It's that many charges. Again, become friends with scientific notation. Not just school friends, hang out with it on the weekends too. Okay? 6.24 times 10 to the 18th, or you have to write out all of the zeros.
3.
Oh wait, we have to write all the zeros in the first one.
No.
No,
If
you
it
guys can
says-
just write this number down.
Fifth
Okay,
place
now
is the
here's the
abbreviated
thing.
unit for charge.
We can have negative and positive charge, and we use the unit coulomb for either negatives or positives. Okay? All right, now we're going to do a couple little problems to get used to this number because it's kind of weird. But all you have to really know is if you have this many charges, you have 1 coulomb. Okay? In a second, we'll do Coulomb's law. Okay? And we'll really use this number. Okay? All right, so let's go to the problems in our notes there. And we'll switch the screen here.
I need to turn it. Should I zoom in?
Okay, so we have this.
Do you have it memorized?
Of course he does. He's a
Usually.
physics teacher.
Okay. All right, now the abbreviation for the unit charge is capital C. That's coulomb.
For Google.
Okay. What about the variable? Let's put another blank here. So the abbreviation for charge is Q. Either little q or capital Q can be used to abbreviate charge. Okay, so what's the variable for velocity?
Meters per second.
That's the unit. What do we abbreviate velocity with?
V.
V. Okay, what's the unit?
Oh, my meters per.
Meters per second, right? Okay, so for charge, we abbreviate the word charge with this Q.
So in equations it would be Q.
In the equations, it will be Q. After your answers will be capital C, coulombs. Okay? All right. So a proton, its charge is measured in coulombs. A proton is positive 1.6 times 10 to the negative 19th coulombs. Very tiny amount of charge. Okay, now here's a mistake I see a lot. People say, oh yeah, a proton's positive, and they'll put a positive right there too. If I put a positive right there, doesn't it make it a huge, huge number?
Really big.
Okay, both of these are to the negative 19th. An electron is just the opposite charge. 1.6 times 10 to the negative 19th coulombs. Okay. We're going to do one example problem together with this, and then you'll try one on your own. If you have a mole of protons, what is their charge? Okay, this word right here. That's another word that represents a number. If you took chemistry, you know what a mole is. If you didn't take chemistry, you're like, what the heck is that? Okay, so a dozen means what?
12.
12. A mole means
13.
6.022 times 10 to the 23rd. Okay, I tell my chemistry students to get a little tattoo right there. Avogadro's number.
That's cheating.
Okay, so that's why Sawyer knew it so quick. Did you hear that? He's got a little. Yeah.
Isn't that cheating?
Is that to the 23rd?
That's to the 23rd. Okay?
Yeah.
It's just a word that means a number. Now, in physics, in this unit, I think this is the only place we will use this number. But I threw it on here to kind of connect it to chemistry, to what you guys know a little bit. Okay, so if we have this many protons, how much charge do we have?
So you have to multiply them.
Yeah, all we have to do is go times 1.6 times 10 to the negative 19. And it is going to be a positive answer because they're protons. Okay, so get out your calculators. I want everybody to punch this in. Okay, so we're going to deal with, in this unit, lots of scientific notation, lots of really big numbers, lots of really small numbers. Do not use times 10 caret ever, ever, ever. You guys already know that. Use what?
E.
E, second comma. Okay?
Why can't I
So
use 10?
here's what you need to type in. E, 23. That's second times or second in the comma. Then we'll hit times. Notice we don't need parentheses when we're multiplying and dividing numbers like this if we use the E key.
What key are you using? Why that key?
Okay? And we get 96,352 coulombs.
That did not work.
Alright, and if we round this to 2 sig figs, we get 96,000 coulombs.
Do you want us to round like that every time, like
Well,
to the nearest whatever?
you've got 2 sig figs here, so technically we should round it to 2 sig figs here. Okay, so here's the deal. That is a lot of coulombs. That is a ton of charge. We usually don't get that much charge hanging out in one place. Okay? Now, is there a mole of protons in this room? Like with all the atoms we have?
Sure.
Definitely. Okay? But is there a mole of protons hanging out by themselves without any electrons? No. In fact, if there were, we'd have some. It'd be dangerous.
Would be
Really
hot.
dangerous.
Why so?
And we'd have some good electrical current that we could create. So a lightning bolt, like an average lightning bolt, is only like 16 coulombs.
Really?
Yeah. So this, not very reasonable. It's not very reasonable to have a mole of protons hanging out in one place, because there's always electrons trying to balance out that charge.
That's crazy.
Okay? In fact, we spend a lot of money taking one type of charge and separating it from another type of charge. Okay? When we can do that, that's when we get things like batteries, generators, etc. Okay? So we'll be dealing with a lot of that stuff. Alright, now how much mass is this? We want the mass of the electrons, we're going to do, or protons, sorry. That's how many we have. And then we need to multiply by the mass of one proton, which you guys have notes up here. Okay, what'd you write down? 1.67
Times 10 to the negative 27.
times 10 to the negative 27. That's in kilograms, so our answer will come out in kilograms.
What E key are you using? The
Okay, I'll show you, watch.
The second double E.
6.022, then you hit second comma. Okay. Okay, so we have 0.001 kilograms of protons. By the way, proton is abbreviated P plus. Electron is abbreviated E minus. And the neutron is N with a little neutral, little zero. Okay? Alright, any questions?
When I put it in like that on my calculator, like you did it on yours, it keeps coming out the wrong answer.
Okay, I can help you. Or you can stop that video.